Gaussian quadrature formula. So this Gaussian quadrature formula is one type of integration which you can use numerical integration. Sure. So in general, integral a to b f of x dx can be expressed as I is equal to 1 to n ci f of xi. So if you are able to express the integral value as a weighted multiplication of the functional value at different variables, so this comes together if it is equal to the integration value, and this equation is called as the Gaussian quadrature equation. This is Gaussian quadrature equation. Here you are expressing this f of x integral value in terms of the undetermined coefficients ci and the location of the x values at different intervals, which are unknown again. So these two are the unknown values which you need to be finding out. So these are the unknown values. So these values actually we have to be finding out in terms of a and b. So this is what we are going to do it. So these are the integral limits. So these unknown values actually we are finding out in terms of a and b, and finally you are getting a simple formula for finding out the integral value, that is sigma I is equal to 1 to n ci f of xi. Now here this I is nothing but here f of x is approximated as a polynomial. So this is approximated as a polynomial, and this polynomial approximated value for which we are trying to find out the integral value as a weighted multiplication of the functional value at different locations given by this xi values. So this is what is called Gaussian quadrature formula for finding out the numerical integration. Now here there are different types of Gaussian quadrature formula. One is 1 point approximated Gaussian quadrature formula. And 2 point, and in general n point. So here actually this is what I have expressed. This is n point Gaussian quadrature equation. This is n point Gaussian quadrature equation. Now from this actually you can derive maybe a 1 point or maybe 2 point or maybe 3 point, but the derivations are a little complicated. But for 1 point actually we can derive and try to understand, and then rest of the things actually you can ignore it. But the methodology I will explain how to derive for each and every one. And here actually when we are doing the computer programming to find out the integral value with the help of this Gaussian quadrature formula, so here actually this methodology doesn't make any sense for us in finding out the integral value. What it matters for us is this xi values and the ci values, whatever is calculated. So these are actually pre-calculated, and then we will be substituting these values directly to find out the integral value in the computer programming. So these values are remembered for calculating the integral value. Got it? Understood? So now actually if you try to approximate as a 1 point Gaussian quadrature is nothing but it is as equivalent as that of trapezoidal rule, what we have found with the help of Newton-Cotes formula, right? So first you note down this. I am going to derive 1 point Gaussian quadrature formula. in 1-point Gaussian quadrature formula, we will be approximating this f of x as a straight line, as if like we have approximated in case of trapezoidal rule. The function is approximated as a straight line. So this straight line is nothing but f of x is equal to a0 plus a1 into x. So this is the approximated straight line. So this one actually, as we know already, with the help of Maclaurin's expansion, you will be able to express any random function in terms of the polynomials with some unknown constants, right? So these are the constants. So this is approximated as a single polynomial, that is of order 1. And in case of 2-point, right, so the same function is getting approximated as, so f of x is equal to a0 plus a1x plus a2x square plus a3x cube. So this is how actually in case of 2-point Gaussian quadrature, it is approximated as a third order polynomial. In general, if you notice, 2-point meaning we are using 3 as the highest power of the polynomial. So here 2n minus 1 is the order of the polynomial. That is the order of the polynomial. So this is n is the point. N-point Gaussian formula. Got it? So here, if you are approximating this function as integral f of x dx between the limits a and b, this is approximated as c1 f of a plus c2 f of b. So this is how actually you can express the 1-point Gaussian quadrature formula if it is approximated as a0 plus a1 into x as the function value. Now this function value, if you put it here, so this one a0 plus a1 into x between the limits a to b, and the integral value is a0 into x plus a1 into x square by 2. And the upper limit is b and the lower limit is a, and this is a0 into b minus a plus a1 into b square minus a square by 2. So this is the integration value. First you note down this, I am going to erase and then find out these unknown values of C1 and C2. So this value is equated to the functional value equivalence. That is, here actually the integral value, integral a0 plus a1 into x dx value between the limits a to b is equal to a0 into b minus a plus a1 into b square minus a square divided by 2. And the same thing actually, as per Gaussian quadrature formula, it should be equal to c1 f of a plus c2 f of b. So this is as per the Gaussian quadrature formula. Here c1 to f of a is the f of x function is given by a0 plus a1 into x. Now if you put x is equal to a, then this is going to be a0 plus a1 into a plus c2 into a0 plus a1 into b. So this is the functional value as per the Gaussian quadrature rule. Now here this is c1 plus c2 times of a0 plus c1 a1 plus c1a plus c2b times a1 is the simplified form. Now the corresponding values on the left side is a0 times of b minus a plus a1 times of b square minus a square by 2. So if you corresponding values equated, so this is equivalent to this one and this is equivalent to this one. So these are the equivalent values. Now from this relation, we can find out the values of C1 and C2 by equating the corresponding values. So C1 plus C2 is equal to B minus A, and C1A plus C2B is equal to B square minus A square by 2. So if you solve these two equations to find the values of C1 and C2. So if you find these values, C1 is equal to C2 is equal to B minus A by 2 are the values. Now from this relation, we can straight away find out integral a to b f of x dx is equivalent to, so C1 value is b minus a by 2 times of f of a plus b minus a by 2 times of f of b. So this way you can straight away find the value of the integration with the help of these constants, whatever we found just now. So this way actually you can straight away find the value of the integration as a constant which we have calculated in terms of a and b, b minus a by 2 getting multiplied by this functional value f of a, and then b minus a by 2 times of f of b, where again this b minus a are the limits and the functional value at this location. So at two intermittent points, that is a and b, with a weighted multiplication of the factors b minus a by 2 and b minus a by 2, this will straight away give the value of the integration, as long as if we approximate this f of x as a straight line. So that way, if you try to integrate this particular function between two different points like this is a and b, and then between these 2 points if you want to find out the integral value, so this you are approximating as a straight line, as if like it is a trapezoid. So in this format you will be finding out the integral value as, so this is b minus a. B minus a is nothing but h. So b minus a by 2 times of, and then the functional value here it is y0 and then plus y1. So this is the value of the integration. This is nothing but the area, and with the help of Newton's course formula also we have got the same thing. And as we know the trapezoidal equation, as we know that trapezoidal area is equivalent to height multiplied by the sum of these sides, that is y0 plus y1 is the sum of these sides, and height 1 by 2 multiplication. So this value is equal to the trapezoidal area even with the Newton course formula, or even with the normal formula, or even with this approximated value of the function as a straight line in case of Gaussian quadrature formula. It will give exactly the same thing. But the complexity in this is identification of these unknown values of C1 and C2. So this is the complexity there. Now here a and b actually we have assumed to be the function is expressed as C1 f of a plus C2 f of b, approximating the function as a straight line. But in case if you wanted to approximate as a third order polynomial, which we call as the 2-point Gaussian quadrature formula, there actually this a, b values also the unknown values. Got it? Understood the concept? Understood? So from this discussion we can conclude that this is an approximated function. So it's not the exact function during that region. So this first actually you need to simplify, and then the limits has to be known. Then only you can apply the Gaussian quadrature formula. So what was just derived now. Similarly, even for the 2-point Gaussian quadrature also, this way we have to derive the formula, and then you have to remember this weighted weights what we are going to multiply for the functional values in the calculation of the integration. So these were calculated once for all before doing the computer programming. Got it? So this is actually one method that is going to be used to find out the integral in case of the numerical methods. Got it? But from UPSC point of view, I don't think it is important for us. So you can note down this. So even the 2-point Gaussian quadrature also, just for the discussion purpose, I will do it. So what we will do is, we will try to approximate the function as a third order polynomial in case of 2-point Gaussian quadrature. So integral a to b f of x dx is approximated as c1 f of x1 plus c2 f of x2. Here this x1, x2 and c1, c2, all the 4 values are unknown here. So here actually f of x is approximated as a0 plus a1 into x plus a2 into x square plus a3 into x cube. So this is how a third order polynomial is getting approximated here. Now here, if you do the integration, integral a to b a0 plus a1 into x plus a2 into x square plus a3 into x cube dx, and this integral value is a0 into x plus a1 into x square by 2 a2 into x cube by 3 plus a3 into x power 4 by 4, and the upper limit is b and the lower limit is a. So if you substitute these values, a0 into b minus a plus a1 by 2 into b square minus a square plus a2 by 3 into b cube minus a cube plus a3 by 4 into b power 4 minus a power 4. Now the corresponding values on the right side are, being f of x is equal to a0 plus a1x plus a2 x square plus a3 x cube, if you substitute here in this equation c1 getting multiplied by f of x1, so this is a0 plus a1 x1 plus a2 x1 square plus a3 x1 cube plus c2 times of a0 plus a1 x2 plus a2 x2 square plus a3 x3 x2 cube. Now here a0 multiplied by c1 plus c2, and then here a1 multiplied by x1 plus x2, c1 x1 plus c2 x2 plus a2 multiplied by c1 x1 square plus c2 x2 square plus a3 multiplied by c1 x1 cube plus c2 x2 cube. So this is one equation on the right side and this is another equation on the left side, and if you try to corresponding values correlate it, that is b minus a is equal to c1 plus c2, and the second one is b square minus a square by 2, this is equal to c1 x1 plus c2 x2. Similarly, next one is a2 factor, that is b cube minus a cube by 3 is equal to c1 x1 square plus c2 x2 square, and then the next one is b power 4 minus a power 4 by 4 equal to, the right side value is this one. So c1 x cube x1 cube plus c2 x2 cube. So we need to be solving these 4 equations. This is equation number 1 and this is equation number 2 and this is equation number 3 and this is equation number 4. So we have to solve all the 4 equations here. Got it? So after solving these equations, we are going to arrive at 4 different values with 4 different unknowns. Those 4 values are c1, c2, x1, x2. So these are the undetermined values which we found just now. So once we got the values, if you want to find out a third order polynomial integral value between the limits a and b, you can straight away make use of this equation with the unknown values whatever we have calculated here. Got it? So this is the 2-point Gaussian quadrature. So I'll just write the formulas, but actually solving these equations actually very tough. First you note down this. I'm just writing those formulas. Just for your understanding, don't try to remember or don't try to know all these things, because actually it is anyway not of much use for us. Got it? Then, so the values of the unknowns are C1, C2 values. After solving all these four equations, you are going to get as C1 equal to C2 equal to B minus A by 2, and the next one, X1 is equal to B minus A by 2 times of minus 1 by root 3 times of plus B plus A by 2. Similarly, X2 equal to B minus A by 2 times 1 by root 3 plus B plus A by 2. So this is the value. Got it? So these are the undetermined values. Once you got this, integral f of x dx between the limits a comma b for an approximated polynomial of third order, this value is going to be c1 f of x1 plus c2 f of x2. So this is 2-point Gaussian quadrature formula. Got it? Okay. So this is about the Gaussian quadrature. I hope you understood the concept and the intent. So do you have any questions on this? Okay. So now we'll start with numerical differentiation. Differential equations, ordinary differential equations. So ordinary differential equation solutions. Now actually, first we need to understand what is meant by solution of a differential equation. So if we have the equation dy by dx is equal to f of x comma y. So let us say this is a differential equation which we wanted to solve. Now the solution of the differential equation is nothing but constructing the original curve from the differential equation. So constructing the original curve is nothing but we wanted to trace the function y is equal to f of x, or actually you wanted to find out some kind of relation between f of x comma y. So this is g of x comma y equal to 0. So this is what you wanted to trace out of this relation which involves differential coefficients. Now here the way we do in case of solution of the differential equations is, now here by definition of the differentiation is nothing but dy by dx. So this dy by dx is nothing but you are trying to find out the ratio between two different values. So this duration is dx, and then here actually this is initial value and this is the final value. So if you call this as y, and this value is going to be y plus delta y or y plus dy, assuming that this is going to be dy. So this vertical difference is dy and the horizontal difference is dx. Now the differentiation is nothing but you are trying to find out the ratio between dy and dx. So this is the ratio. So here actually dx is almost 0. That is the assumption here what we are making. So dy by dx is the ratio what we found in terms of the function as f dash of x, being this is y is equal to f of x as a function. So this is f dash of x value you are expressing as dy by dx. Now here if you replace this, if you put this value here, dy can be approximated as f dash of x into dx. So dy is equal to f dash of x into dx. What is here graphically we can see is, this is the value of dy, and this dy value we will be able to find out with the help of this dx and the derivative value at this particular location. So the derivative value is f dash of x and getting multiplied by this dx value. So this will give the difference between these 2 points. Now the construction of the curve, meaning from this location of y, what should be the value of y plus delta y? That's what is nothing but the curve during that particular region of here to here. So maybe this is very small region, but still actually this is important for us. And then from there actually you are trying to construct the next value of y with the help of f dash of x at that location getting multiplied by the dx duration, which is the strip what we are considering as the different intervals, which we call popularly as this value as h for us. So this h getting multiplied by the slope value at this location will give the difference of the values between this y and the next y. Now you are able to find out this y plus delta y as, so initial y value plus this f dash of x getting multiplied by dx. So this dx is h for us, and this is y plus delta y we need. So the next value, this value we call this as y1, and then y1 can be equal to y plus f dash of x into h. This is the initial value y0. So from y0 plus h into f dash of x will give the y1 value, which is nothing but from this value, if you know the slope at this location and if you know the strip width, you will be able to find out the next y value. Now from here actually, if you want to consider next strip this way, this is again the h value, and then this is y2 for us. So this y2 from y1, it is at a height of dy at that location. dy is dependent on the slope at that location and the strip width. Strip width anyway fixed, so that we are making equal intervals. That means h is anyway constant, and what is variable is the slope at that particular point, which you can calculate from the particular function y is equal to f of x. So this slope y2 is equal to y1 plus h times of f dash of x again at, this is at x0 and this is at x1. Got it? So f dash of x at x1, or in general you can write this as, this is x0 and this is x1. So you can remove this. Similarly, y3 equal to y2 plus h into f dash of x2. So this way you can reconstruct. So from this point you constructed this value, from this point you constructed this value, from this point you will construct the next value, and then if you try to trace all these points, is nothing but you will be able to trace the curve as if like y is equal to f of x graph. So that is nothing but you are identifying the solution of the function if you know the derivative of the function at that location. So in solving the differential equation dy by dx is equal to f of x comma y, you will be exactly adopting the same procedure to reconstruct back the curve. So this methodology, so first actually it was identified by Euler. So this is Euler's method of solution of the D. Got it? So this methodology, the same thing is adapted by Euler. So this one, dy by dx actually, even it may be a function of x or maybe a function of y. So as you know, dy by dx is equal to f of x comma y. If you know the values of x comma y at one particular location, you will be able to calculate the f dash of x in terms of dy by dx is equal to f of x naught y naught. So the slope at this location. So if I draw this graph as, suppose if this is the curve, and then from here to here actually I wanted to trace the curve, and here actually what I will do is I will divide this into multiple parts. So each part of width h, and then what I will do is this function is given by, so here dy by dx is equal to f of xy is the equation which we need to be solving. For that actually let us say this is x0 and then this value is y0 obviously. So here the slope of the tangent from this location is nothing but, so dy by dx is nothing but f of x naught comma y naught is the value of this slope at this location. Now, if you want to find the value of this location y1 can be approximated as y naught plus h times of f of x naught comma y naught. Because f of x naught y naught is the slope of the curve at this location from the differential equation of dy by dx is equal to f of x comma y. Got it? So you will be able to find out the next value of y1, and from here if you want to find out the next value as y2, so y2 can be given as y1 plus h into f of x1 comma y1. So as you have already calculated this value as x1, which is equal to x naught plus h, and the functional value is y1. So this y1 which we have already calculated here with the formula, and then this value and this value you can make use to calculate the next value of y, which is nothing but y2 here. This y2 can be given as y1 plus h times of f of x1 y1. Similarly, y3 can be calculated as y2 plus h times of f of x2 y2. x2 is nothing but x naught plus 2h. So because each strip is separated by a distance of h, so this is x naught, this is x naught plus h, this is x naught plus 2h, and in general, so last value is x naught plus nh, because you have divided this into n different intervals. Got it? So this method is called as the Euler's method of solving the ordinary differential equation of the form dy by dx is equal to f of xy. Got it? Understood? So in general, Euler's method, right? So the way we reconstruct the curve is, so from here actually, so this is the curve actually which we wanted to trace. Here you will be drawing a tangent like this, and this is the tangent at this location. And then here actually from this tangent slope, so this tangent slope, this is x naught and this value is y naught. So this is the height as the y naught. So the tangent value dy by dx is equal to f of x comma y is the curve actually which we wanted to trace. So for that actually the tangent slope dy by dx at x naught and y naught, so this value is f of x naught comma y naught. And then you tried approximating the curve. Maybe the curve is of this particular format, but you tried approximating this curve as a straight line at this location by taking this tangent for the entire strip of this length. So this is the tangent you are considering here. Now here what you will do is, here again once you got the value of y1, here based on this equation again you are trying to draw a tangent to the curve at that location like this. So you tried tracing this point instead of the actual curve, and this error is coming just because of the reason that, so that is you have used the strips of a definite value of the width. But if the value of the width is very less, then actually you will be able to quickly trace or exactly trace the curve. But being the strip width is more, you will not be able to trace 100% accurately. So in the numerical methods, there will always be an error, because actually you are trying to approximate as a strip rather than a zero width. Hence actually the curve what we are going to trace, right? So it will always have certain error. So here you are trying to approximate this as one more tangent. So this tangent direction is this one, and here the curve is like this. And then again with this tangent actually you tried calculating the next value here. Again for this particular curve you will try to trace the tangent direction like this and then try to find out the value like this. So like this actually you are trying to approximate as a tangent at that location, and then keep on continue to trace the curve, and then finally you might be tracing this curve, but ideal curve may be of this particular format. Got it? Or vice versa also, depending upon the type of curve it is going to be. So the curve may be that side or this side depending upon the type of curve. Got it? So finally, so this is the approximated curve. and this may be the actual curve. So this is how you will be finding out the value of the y values, which you can make use to reconstruct back the original curve from the differential equation like this. Now here actually, when we wanted to find out the curve values or the y values depending upon the x values, what you are going to do is you will try to prepare a table. So the table is x naught value or x value and the y value, and then dy by dx value. So this is f of x comma y value, and then from here actually you have to find out the y new is going to be y old plus h times of, so f of x naught x comma y. So this value actually you have to prepare a table, and then here actually x naught and here y naught, and here this is going to be dy by dx is f of x naught y naught, and this is y new or y1 is equal to y naught plus h times of f of x naught comma y naught. From this actually you will be calculating the next value as x naught plus h, and this is going to be y1, and this value is going to be, so f of x1 x naught plus h comma y1, and this value is y2 is equal to y1 plus h times of f of x naught plus h comma y1. So this is how actually you will try to fill this table to find out the unknown values of y here. So these unknown values and the x values, whatever you have selected, you will make use of those points. That is this point, this point, this point, this point, and you will try to trace that curve like that. So tracing that curve is nothing but the solution of the differential equation, which you have calculated with the help of this Euler's method. Now there is something called the extension of the Euler's method or the corrected Euler's method. Here actually what we are trying to approximate here it is, here the slope whatever we calculated, you are trying to make use of the slope at this point to identify the next value. But actually if the curve is of this particular format, then actually you cannot think that actually the slope whatever is there here, it is going to be there even here as well. So there will be a difference of slope between these two. So the corrected Euler's method is, what we are going to take is, you will take the slope at this location, that is the initial point, and then you take the slope at the next point also after calculating the first iteration. That is, you have considered x naught and y naught, and you have calculated f of x naught and y naught, which is nothing but the slope, and then you have calculated y1 value. Now once you calculate the y1 value, don't go to the next value. So here itself, so it will be, this y1 value will be corrected again for a better accuracy by considering the slope at the other point, that is at x naught plus h and y. So x naught plus h and y1, there actually you will try to calculate the slope again and take the average of the slopes between this one, and then that average will be considered for the next value to correct the value of y1. So here h is no more getting multiplied by f of x naught y naught. It is going to be h by 2 times of f of x naught y naught comma f of x naught plus h comma y1. So these two values actually we have to take the average of it and then try to get the value of y1 again. So then again make use of this y1 value in the next iteration again to correct same y1. So depending upon the accuracy requirement, if you get in consequent iterations, if you are going to get the same y1 value, then you are going to stop there, assuming that you have achieved 100% accuracy or whatever the desired accuracy you need. So once you got that value of y1, then go to next value of calculation of y1, y2. Got it? So y1 itself actually it will take 2-3 iterations again to get corrected to an accurate value. So by assuming the slopes or the average of the slopes here and here, so instead of one slope considering here, you will be taking the average of these two slopes and then try to adapt and to calculate the value of y1. So this procedure is getting repeated so that you will get a better accurate value of y1. Once you got enough accuracy for y1, you will go to the next step to calculate for y2, and the same procedure is repeated for getting a better accuracy for y2 as well. Got it? So first we will solve a problem with normal Euler's equation, and then once you got understanding to the Euler's equation, then we can go to one more problem based on the extension of the Euler's theorem. So that is the corrected method of Euler's method. Got it? So first you note down this. I'm going to give you a problem for you. So note down this problem. Using Euler's method, find an approximate value of y. Using Euler's method, find an approximated value of y corresponding to x is equal to 1 given that dy by dx is equal to x plus y. Given that dy by dx equal to x plus y and y is equal to 1 when x is equal to 0. So here actually he asked us to find out, using Euler's method, find an approximated value of y corresponding to x is equal to 1. So here the initial values of x naught comma y naught value he has given as 0 comma 1. So this is the initial value what he has given. Now he asked us to find out the value of the y value at x is equal to 1. So that means from 0 to 1, if you notice, so dy by dx is equal to x plus y. Let us say this is the curve you can think of. Now in this curve at x is equal to 0, this value is 1 what he has given. This is 0 comma 1. And then here actually we need to be finding out at x is equal to 1. For that what you need to do is you have to divide this entire region of 0 to 1 into multiple parts depending upon your accuracy requirement. So you can make 10 different intervals and then you can calculate it. Or you can make 20 different intervals and you can still calculate it for a better accuracy. So for us actually, we can think of 10 different parts like this. So like this actually, you can divide into 10 different parts.